In this video, I'm going to go over number 2 of the AP Physics C-Free response for 2008. Okay, so the second question says, the horizontal uniform rod shown above has length 0.6 meters and a mass of 2 kilograms. The left end of the rod is attached to a vertical support by a frictionless hinge that allows the rod to swing up or down. The right end of the rod is supported by a cord that makes an angle of 30 degrees with the rod. A spring scale of negligible mass measures the tension in the cord. A 0.5 kilogram block is also attached to the right end of the rod. So here's the first part of the question. It asks you to draw and label the vectors to represent all the forces acting on the rod. Well, the rod obviously has the force of gravity acting on it, as all objects do. The vector should be placed at the center of mass of the rod, which is right there. You know the center of mass has to be at the center of the rod since the rod is of uniform mass distribution. We also have the weight of the block acting on the very end of the rod. There's also tension in the rope. Remember that tension always pulls on an object, it never pushes. So the arrow is going to point away from the edge of the rod, since it's pulling the rod. The hinge is keeping the left side of the rod from falling down. So we have a force pointing up. The rod also opposes the horizontal component of the tension force that is pulling the rod to the left, by imposing a force to the right. And this ensures that there is no motion in the horizontal axis. If we add the vectors of the horizontal and the vertical components of the hinge force, we can get a total force vector in the top right direction. Part B asks us to find the reading on the spring scale, which is basically another way of asking us to find the tension in the string. So the rod isn't moving. Therefore, the net torque on this rod is 0. Torque is equal to the moment of inertia times the angular acceleration, but if the rod isn't moving, the angular acceleration is 0, therefore making the net torque 0. To find the expression for torque, you have to first determine your pivot point. To make things easy, I'm going to pick the very left of the rod as the pivot point. I took my point where the hinge force originates, because that way I can say that the torque exerted by the hinge force is 0. And that makes sense because the force, which is h, times the distance, which will always be 0, will always result in a torque exerted by the hinge force of 0. So we won't even have to factor the effect of the hinge force into our calculations for torque. Now let's look at the forces that act in the vertical direction. We have the vertical component of the tension force. Remember, it was given in the question that the angle the tension force makes with the rod is 30 degrees. So that's why the vertical component is equal to T sine 30. Remember the formula for torque. Torque is equal to Fd, where F is the force and d is the distance the force is from the pivot point. Okay, so we've got T sine 30. Now how far away is this point from the pivot point? Well, it's just the length of the rod, L, right? There are two other forces acting in the vertical directions. We have the weight of the rod, which is at a distance of L over 2 away from the pivot point, since the center of mass of the rod is at the midpoint of the rod. We also have the weight of the block, which is at a distance of L away from the pivot point. So the torque exerted by the weight of the rod is big M times GL over 2. And the torque exerted by the block is small m times G times L. We put minus signs here because the upward direction is positive, which is why T sine 30 does not have a negative sign in front of it. MGL over 2 and small m times GL are in the downwards direction, which is why we have minus signs here. So the net torque is equal to T sine 30 minus big M times GL over 2 minus small m times GL, which is all equal to 0. Then we just have to solve for T. We can substitute the appropriate values to find the final value of tension, which is 29 newtons. We're not going to consider the horizontal forces or the horizontal components of the forces because these forces go through the pivot point and therefore have no effect on the torque. If you look at this diagram, it can kind of make sense because if you push this rod from this direction, no matter how hard you push, the rod isn't going to move up. If you push it from this direction, however, the rod will move in this direction. The third part of the question asks us to calculate the rotational inertia of the rod block system about the hinge, given that the rotational inertia of a rod about its center is 1 over 12 ml squared. So we have to find the rotational inertia of the rod block system, which I will call I sub s. The rotational inertia of the whole system has to be the sum of the rotational inertias of the rod and of the hanging block. So I'll call the rotational inertia of the rod IR, and I'll call the rotational inertia of the block IB. So IS is equal to IR plus IB. Let's first take a look at IR. We know that the rotational inertia of the rod about its center is 1 over 12 ml squared, as given in the question. What we want to know is the rotational inertia of the rod about the hinge at the left end of the rod. To do this, we use the parallel axis theorem. Remember that the parallel axis theorem states that to find the rotational inertia around any axis parallel to the axis at the center of mass, you have to add the rotational inertia at the center of mass with md squared. So in this case, the rotational inertia around the edge of the rod is equal to the rotational inertia around the center of mass, which is 1 over 12 ml squared, added to m times the square of L over 2. And remember, it's L over 2 because that is the distance between the two axes, as you can see in this diagram. If you simplify all this, you get 1 over 3 ml squared. Okay, now for the moment of inertia of the block. We can assume the block to be a point mass. So the mass is just small m, not to be confused with the capitalized M for the mass of the rod. The distance from the axis of interest is L. 1 over 3 ml squared plus small m times L squared will be the total moment of inertia. Plug in the numbers to get 0.42 kilograms meters squared. Okay, now for the moment of inertia of the block. We can assume the block to be a point mass. So the mass is just small m, not to be confused with the capitalized M for the mass of the rod. The distance from the axis of interest is L. That would make the moment of inertia of the block to be simply ml squared. So the total moment of inertia would be 1 over 3 ml squared plus small m times L squared. If you plug in the appropriate numbers, you get 0.42 kilograms meters squared. Finally, part D says, if the cord that supports the rod is cut near the end of the rod, calculate the initial angular acceleration of the rod block system about the hinge. So now that the cord is cut, the torque is no longer zero, since the rod will be moving. Torque is equal to the moment of inertia of the system times the angular acceleration. We also have to find the appropriate equation for the torque regarding the two parts of the system, the rod and the block. The torque about the hinge due to the block is just mgl. The torque about the hinge for the rod is big M times g times L over 2. So the net torque is equal to the mass of the block times gl plus the mass of the rod times gl over 2, which is all equal to I alpha. Solve for alpha. If you substitute the appropriate numbers to find you'll find an angular acceleration of 21 radians per second squared. So we know that g is 9.8 meters per second squared, L and the masses were given in the question, and I we found in part C. And that's it.